Hi everyone. Good to see you tonight, or this morning, or whatever time it is. I'm sorry, I'm actually stuck on an airplane right now. I'm flying from Shanghai to Los Angeles after giving a bunch of talks all through China for the last week. But welcome to our YouTube channel and welcome to our live solve. We're really happy to work with Math League. They have a good set of questions that they put out every single month, and this gives everyone a chance to think about some interesting questions on a regular basis. We're lucky tonight to have some wonderful stars from our program. We have a high school program where there are math geniuses who are trained by professional actors to be both mathy and interesting. And they're going to take it from here. Toss it to them now. Take care. See you. Hi everyone. Good to see you tonight, or this morning, or whatever time it is. Good to see you tonight, or this morning, or whatever time it is. I'm sorry, I'm actually stuck on an airplane right now. I'm flying from Shanghai to Los Angeles after giving a bunch of talks all through China for the last week. But welcome to our
because it rings once every 5 minutes. So 15 minus 5 is equal to 10. So yeah, so that's our answer. It's going to take 10 minutes after alarm B first rings for both alarms to ring simultaneously. Alright, okay, so to check that that's the right answer. Alright, okay, so nice. The answer is 10. Alright. Is everything alright over there now, Luke?
Yeah, sorry, I think everything's all right over here now. So I will go ahead and try and solve the next problem. So this is problem 9 now. And, ooh, it looks a little funky on my screen. Hopefully that should be okay. But the problem says a square has side length 10. Point M is the midpoint of side AB, and line segments DM and BC are extended to meet at point N. What is the area of pentagon AMNCD? All right, so that is a little confusing, so I think we're just going to make a new slide here and try and add a drawing. So we have a square of side length 10, and then going back to the problem, the midpoint of side AB is M. So we're going to label everything. A, here, B, and then we have C and D. And the midpoint of side AB is going to be M. All right, now going back to the problem. Line segments DM and BC are extended to meet at point N. What is the area of pentagon AMNCD? DM and BC are extended to meet at N. And here's the point N. So now we're asked, what is the area of pentagon AMNCD? All right, so this seems a little difficult, but hopefully we should be able to get the handle of this. The first thing I noticed immediately is that this is the midpoint, right? So we know that AM is equal to 5, and MI is also equal to 5. And we also know that AD is equal to 10, and BC is equal to 10. All right, now one other thing I see in this shape is that it seems that these two triangles are similar. AMD is similar to BMN. All right, my B looks a little bit confusing there, so I'll fix that real quick. So it appears, I'll write it down here. It appears that triangle BMN is congruent to triangle AMD. Now to prove that this is true, you see that they have these vertical angles right here, and they also have this 5 length right here, 5 and 5. And finally, they have one more angle. Actually, we're not going to care about the sides. All of the angles are the same because this angle right here is 90 degrees. This angle up here is 90 degrees. This angle is vertical angles, so that's just two angles, and as well as the angle over here. So similar triangles, and then we know they're congruent because MB is equal to MA. So we know that these two triangles are congruent, and we know that BN is equal to 10. So now we see that the area of this pentagon is really just the area of this square, and then we add this triangle over here, and that's going to make the area of the pentagon. So the area of the square is equal to S squared, or that side length is going to be 10 in this case. So 10 squared is the size of the square, and then we have to add the size of this triangle right here. And that's going to be 10 times 5, and then you have to divide by 2 because it's a triangle. And when we add all this up, I'm not going to do it all manually. I'm just going to write it here. We get 125, like I said, like I see people in the chat already got, which is really great. So 125, and let's check if that is correct. And indeed, the answer is 125. And I'll let Eric go on and take the next question.
All right, okay, great. So on to question 11. This question, it seems like I'm getting all the combinatorics questions. So this one is, how many ways can a committee of 5 people be chosen from a group of 10 people, given that 2 specific people, Alice and Bob, cannot both go on the same committee? All right, okay. So I think this is another good chance to do complementary counting, because whenever they tell me I can't do something or you don't want to do something, we always just try to do it and we just subtract that from the total, right? So the number of ways, so let's start with the total number of ways we could form a 5-person committee from a group of 10 people without any restrictions. So like almost by definition, that's going to be 10 choose 5. So this could be our total. This could be our total. All right. Okay, now let's suppose that we want to put Alice and Bob in the same committee. If we want to put Alice and Bob, if we want to put both Alice and Bob on the committee, then there's going to be that they're just going to take up 2 of the spots immediately, right? So really we could think about forming a 3-person committee. So 3 committee from 8 people. All right. And then after we form that 3-person committee, we just add Alice and Bob onto there. So this could be, again, this is just going to be another binomial coefficient. So that's going to be 8 choose 3 this time. All right, so there's going to be 8 choose 3 ways to choose that 3-person committee from 8 people, and then adding Alice and Bob onto it. But this is what we don't want, right? Because we actually don't want Alice and Bob to be in the same committee. And so we subtract that from the total. And now to do some calculations, 10 times 9 times 8 times 7 times 6 divided by 5 times 4 times 3 times 2. Let's see, to compute that, we could cancel out that 6 there, cancel out that 8 with a 2, cancel out the 10 with a 2. So that could give us 126. And then minus 8 choose 3 is going to be 8 times 7 times 6 divided by 3 times 2. We cancel out the 6. That's a minus 56. And the answer, if I didn't make a mistake, should be 70. Ooh, it says, some people are saying that 10 choose 5 is actually 252, which might very well be true. Okay, you're right. So that's my bad. I computed 10 choose 5 wrong. That's because I forgot to multiply by 2, so yeah, you're right. 10 choose 5 should actually be 252. So let me correct that. Right, so 252. And then we subtract 56. And yeah, so that's going to end up being 196, which, yep, I see everyone is getting in the chat, probably way before me, which is really great. And we could check the answer, which is indeed 196. All right, okay, back to you, Luke.
Yeah, great job, Eric. That was a really cool problem. I really liked it. All right, so now on to the 13th sprint round problem. And this problem reads, the product 23 times 38 times 51 times 77 times 95 is divisible by the square of exactly one prime number. What is that prime? All right, so I know a lot of these numbers look prime, but I think the best way to figure out the answer to this problem is just find the prime factorization of the number first, and then we can immediately see which number it is that has a square in the prime factorization. All right, so 23 is prime. If you guys don't know that, then you can easily check it by just checking all the numbers up to 23 to see if it's divisible by any of those. And 23 is prime. So 23 is in the prime factorization. Now the prime factorization of 38 is 2 times 19. So our prime factorization now looks like 23 times 2 times 19. We're just breaking up each of these numbers into their primes. The next number is 51. And 51 is actually equal to 3 times 17. I kind of know this because just being around numbers a lot, I guess. But you can check all of these by going, is 1 divisible by, oh, not 1, is 2 divisible by 51? Is 3 divisible by 51? And that kind of thing, until you find something that's divisible, or until you don't, and you realize that it's prime. So going on to the next number, 77. Hopefully most of us know that this is 7 times 11, and those are the 2 primes. Finally, we have 95, and we can easily see that 5 is a divisor of 95, so then we have 5 times 19. And those are going to be all the primes. So now we just have to look for a duplicate among these primes. And if we look carefully enough, I think we see 19 as that duplicate. So 19 is going to be the only number that is a square prime divisor of this product. So 19 will indeed be our answer. And I see many people in the chat got that correct. So Good job, everybody, and we'll check our answer, and yep, it's 19. So back over to you, Eric, for the next sprint round problem.
All right, yeah, that was cool. All right, but now this time we're moving on to some geometry. Oh, I guess we already did touch on geometry. It's the first time I get to go at geometry today, though. So this question reads, a circle with area k pi is inscribed in a rhombus with side length 41 and area 720. What is k? And express your answer in the common fraction. So first, probably a good habit in geometry is to draw a diagram. So let me do that. All right. So this diagram will probably not be to scale or like not even be like proportionate to anything. All right, so hopefully that is a good rhombus. And so we're going to have a circle inscribed in it. So let me try my best to draw a circle inscribed in it. These are always tough though. Right. Okay, so hopefully that's all right. So we have the circle inscribed in it. And so now what I always like to do at the start of these like circle problems is to draw a radius, and usually I want to draw it to a tangent because we always know that the radius from the center of the circle to a line that's tangent to the circle is always going to be perpendicular to that line. So immediately we're going to get some nice right angles. All right, so let me make that right angle a little bit clearer. Okay, so now what I'm thinking, so first let me write some of these numbers, these side lengths. So all of these are 41 because it's a rhombus. All right, so now what I'm thinking is I want to use the fact that the area is 720, but the rhombus is a little bit unwieldy. So I'm thinking we split it up into some triangles, and then we just figure out the area of each of those. We figure out the area of each of those smaller triangles from the top. So that's what I'm going to do. I'm going to draw these lines that go through the middle, through the center of our rhombus, and we split our rhombus into these 4 right triangles. All right, okay, and now we can compute the area of each of these small triangles because they're all going to be congruent, right? We have a rhombus, everything's symmetrical, so the area of all of these triangles will also be the same. So the area of each of these triangles are 720 divided by 4, which is equal to 180. And what I'm noticing, what's more, since we want to find the area of the circle, what we're really interested in is what the length of this radius is. And I'm noticing that this radius is perpendicular to the side length. So, or in other words, when I think about perpendiculars and I think about triangles, that means that the radius is the height of this triangle. And I know the formula for the area of a triangle is area is equal to 1/2 base times height. In this case, we could say height is the radius. So radius times, and also the base is going to be 41 because that's given in the answer. Given in the question. So that's 1/2 times r times 41. And we also know the area is going to be 180. So now we have an equation with one variable and only one equation. So we know we're going to be we're close to our answer because we could just solve for r. So now we're going to be able to compute the r is equal to 360 divided by 41. Okay. All right. So r is equal to 360 divided by 41. And yeah, I agree with some people in the chat that this is a little bit of an ugly fraction, but I guess we get what we get. So 360 divided by 41, and to compute the area of the circle, we just square that number. Wow, that is actually pretty ugly, I'm not going to lie, but... Alright, so we're just going to square that number and compute that as a common fraction. That is pretty ugly, I'm not going to lie. Did I make any mistake, Luke?
No, I think you got it exactly right. I did the same calculations and I got the same value for R. And what everyone says in chat, so I think you just have to do the calculation, I guess.
Okay, that's that's a win and that's like a loss at the same time. So 36, um, let's see, 36 times 36. Let's see, that's 1296. Sorry, I'm just gonna skip some of the like the long multiplication. And then 41 squared. Uh, once, shoot, I did not know this one in my head. So that's equal to 41 times 164. Okay, so that's equal to 1681. All right, okay, so our answer is going to be 129600 divided by 1681, which I think a lot of people in the chat got as well. All right, okay, and we could check our answer. Hopefully this is right. Okay, yeah, so it is 129600 divided by 1681. All right, that was pretty cool. I'll move back to you, Luke.
Yeah. All right, now our next problem is the 17th sprint problem. And the problem says, how many lists of three not necessarily distinct positive integers satisfy the properties below? The last number in the list is 2025. Each of the first two numbers in the list is a positive divisor of the number immediately after it. All right, this is a very interesting problem. So I'm just going to call these three numbers A, B, and 2025. And the most important thing I think in this problem is going to be finding the prime factorization of 2025. Because in order for a number to be a divisor of the other number, we kind of need to know the prime factorization. So if no one knows the prime factorization of 2025 off the top of their head, I kind of have it memorized, and that's just 3 to the 4 times 2 to the 5. Sorry, not 2 to the 5, 5 to the 2. And I think what we're going to do in this, we need for a number to be a divisor of the other number, we need the exponent in both the 3 and the 5 to be less. For example, we need b to be something like 3 to the 3 times 5 to the 1. And the reason why this works is because 5 to the 1, 1 is less than 2, and 3 to the 3, 3 is less than 4. So when you divide 3 to the 4 times 5 squared over this number, you get an integer, and that means that it's going to be a divisor. So we can also have it equal to the number. So we could have b be 3 to the 4, and it would still be a divisor. So that's kind of what I'm looking at right here. We could even have it be 3 to the 4 times 5 squared, but we just need it to be less or equal to. And we can kind of treat the 3 to the 4 and the 5 to the squared separately. We can say, we'll multiply how many ways we can rearrange the 4 powers of 3 and multiply the number of ways we can arrange the 2 powers of 5. And when we multiply those together, we should get our answer. So we have 4 powers of 3 that we can kind of distribute among these two, b and a. We could either, let's just write out a bunch of examples of these exponents. We could have a equal to 0 and b equal to 0, or we could, when a is equal to 0, we could have b equal to 1, 2, or 3, or 4. If a is equal to 1, b could be equal to 1, 2, 3, or 4. And what I mean by b equal to these, I don't mean like actually equal to. I mean the power of 3 that b contains is equal to one of these things. So I know that might be a little bit confusing, but when we shape it all out in the end, hopefully it should make sense. So when the power of 3 in a is equal to 2, we could have the power of 3 in b be equal to 2, 3, or 4. When we have the power of 3 in a equal to 3, we could have the power of 3 in b be equal to 3 or 4. And finally, when we have the power of a equal to 4 in a, we could have the power of 4 in b only equal to 4. So there's a little pattern here, and I don't know if you guys noticed it, but there are 5 options for b when a is equal to 0, 4 when a is equal to 1, 3, 2, and 1, and so on. And when you sum all those up, it's really just 5 plus 4 plus 3 plus 2 plus 1, which I'll get to in a second, but I'm trying to erase all my work because I think you guys already saw that pattern. So the total number of options for the power of 3 when we take both a and b into account is going to be 5 plus 4 plus 3 plus 2 plus 1 because of the work that we just did. So when we add all of these up together, we're going to get 15, I believe. Yes. This is 6, this is 6, this is 3. That's going to be 15. All right. So now we just need to figure out how many possibilities there are for the 5 squared between a and b. So let's do kind of a similar thing. When a is equal to 0, b can be equal to 0, 1, or 2. And now we kind of know what's going to happen from here. It's just going to be 3, 2, and then 1. So we can kind of jump a little bit here and say that the number of options for the power of 5 when we take both a and b into consideration is going to be equal to 6. So we have 15 and we have 6. And as I said earlier, these are independent things that we are considering. We are considering the 3 exponent and the 5 exponent. So 15 times 6 is going to equal 90, and that is going to be our final answer. Hopefully I didn't make any mistakes, and I see a lot of answers in the chat that also say 90. So yep, the answer is indeed 90. All right, I'll pass it back to Eric for the next problem.
All right, yeah, that was a tough one. Okay, so this one is also going to be dealing with 2025. So this is, what is the sum of the positive divisors of 2025? All right, so this is going to deal with some pretty big numbers. We already saw that the prime factorization of 2025 is equal to 3 to the 4 times 5 squared. And that's going to be, if we want to list out all those positive divisors, that's going to take a while. So what I want to do real quick is I want to choose a smaller number to try out real quick. Because we know that 2020, there's probably nothing particularly special about 2025 other than it's our year. So let's take, let's see, what about 12? All right, so what I'm noticing with 12 is, all right, so first let me write prime factorization. That's 2 squared times 3. And I can sum its divisors. Let's sum its divisors based, like, let's order the sum of the divisors based on, how about the, whether or not it has 3 in it. So if it doesn't have 3, then we're going to have 1 plus 2 plus 4. So those are the divisors without 3 in it. And then once we add 3 in it, we're going to have, let's see, we're going to have 3 times 1 plus 3 times 2 plus 3 times 4. All right, okay, so now this is really interesting because what we notice is that we have this 1, 2, and 4 on the left side, and we also have 1, 2, and 4 on the right side. And when we have that, we could just lift that out, right? So let's try taking out that 1 plus 2 plus 4, and we're going to have just 1 first, 1 because it's 1 plus 2 plus 4, and we have 3 next because we're multiplying by 3 to each of those divisors. Alright, so this tells us that the sum of the divisors is actually equal to 1 plus 2 plus 4 times 1 plus 3, and we could really quickly calculate that that's equal to 4 times 7, which is 28. Alright, okay, so that was a small example, right? And now I think we have all the tools we need to attack that really big example, which is our problem, 2025. So I'll start a blank screen, and we could try it. So 2025 factors to 3 to the 4 times 5 squared, and then we could use the same method. We could do the case based on the number of 5s we have. So we'll have 1 plus 3 squared times 3 cubed plus 3 to the 4. And because I don't want to write this out a bunch of times, I'm just going to call this equal to, like, let's say capital A. So that's equal to A. And our divisors are going to then be A plus 5 times A plus 5 squared times A. And now we factor out that, we factor out the A from here, so we get A times 1 plus 5 squared. Alright, okay, now this is really nice because now instead of calculating a big sum, we can now calculate a product between A and 1 plus 5 squared. And so A is equal to 1 plus 3 squared plus 3 cubed plus 3 to the 4, and then times 1 plus 5 squared. Alright, so this is still going to be a uncomfortable amount of computation, but it's a lot better than what we were doing before. Real quick, I do want to use the fact that 1 plus 3 plus 3 squared plus 3 cubed plus 3 to the fourth is actually a geometric sequence, or sorry, geometric series, and we can use the formula for geometric series to compute that this is equal to 3 to the 5 minus 1 divided by 3 minus 1. Right, and so this, if you don't know this, it's fine. You could just compute what the sum is equal to and everything will be alright. Or we use geometric series and we find that 3 to the 5 minus 1 is 242 divided by 2 is equal to 121. Alright, so this means that the sum of divisors is equal to 121 times 1 plus 5 squared, and that's equal to 31. Shoot. Alright, so now we need to do another multiplication. 121 times 31, it's 121, and then 363. We add that together to get 1573. So 3751 is going to be the sum of our divisors. And yeah, I see some people in the chat got that as well, so let's see if that's our answer. Alright, perfect, 3751. Alright, okay, I'll move back to you, Luke.
Yeah. Alright, really good job on that problem. That was very cool. I liked your explanation of the formula itself, which is awesome. Alright, now on to some geometry again, and this is going to be three-dimensional geometry, which is quite tricky for everyone, including myself, so hopefully we can solve this though. Tetrahedron ABCD has edge lengths CD equals 24 and BC equals BD equals 15. AC equals AD equals 20 and AB is equal to square root of 337. All right. There are a couple things I notice here first. So there are a couple triangles in a tetrahedron, right? Actually, there are a lot of triangles. First, I'm just going to draw a tetrahedron, right? My incredible three-dimensional geometry drawing skills, which I do not have, are going to come in clutch here. That is my beautiful tetrahedron. It kind of looks like it, you know, a little bit. But the first thing I noticed is that there are two isosceles triangles. So let's look at triangle BCD here. Triangle BCD. Triangle BCD has CD equals 24, BC equals 15, and BD also equal to 15. So CD and B. Sorry, that was not meant to be. That was meant to be D over here. All right, we know that this length right here is 24, this length is 15, and this length is also 15. Now there's one more thing I want to notice about this triangle. It's not only isosceles, but if we draw this altitude right here, we split this up into 12 and 12, right? And we also know that this length right here is 9. So we know a lot more about this triangle than we'd expect. And now I think we can solve the area of this triangle, then multiply it by the height of the tetrahedron itself, and then we can use the formula that we have for this, the volume of a tetrahedron, which is going to be the base times the height divided by 3. And once we do that, I think that will bring us our answer. So the area of this triangle itself is going to be 24 times 9, and this is equal to 24 times 9 divided by 2. Can't forget to divide by 2. And this is equal to 108. 108. All right, now we just need to find the height. I'm going to open a new slide for this because we're getting a little bit messy now. All right, so we have this BCD triangle right here. B, C, and D. And we know that CA is equal to AD is equal to 20, and AB is equal to the square root of 337. So I'm going to go back a second here. I'm going to draw it in the center here. This is going to be BCD, and then we have a point up here. We're going to draw, that's going to be A, and it looks a little bit like not very good, but it's okay. This is going to be point A, this is going to be point C, D, and B. So we know that both of these are equal to 20, 20, and 20. And the other side is going to be equal to square root of 337. Square root of 337. All right, so that's our triangle, and we can actually figure out this altitude right here. And because all of these side lengths are equal, DB is equal to CB, and all of these things are symmetrical, which means that when we put A, B, and A, let's just name this point E on a line, this point from B to E is actually going to be the altitude of that triangle. And we already know that altitude. That length's going to be 9. So we know that that's 9. The other side is square root of 337 of this triangle. And finally, this side right here is going to have 20 as the hypotenuse of this right triangle. And then this base right here, if you don't remember, is 12. So we know that AE is actually, in fact, 16. So 16 and 9 are our two sides. So now we have a little triangle here, and it's going to be A, E, and B on the other side. A is right here, E, and B. 9, 16, and square root of 337. So now we need to find the height of this triangle. And before we start dropping altitudes and trying to find the height, it seems to me that maybe this is a right triangle. So let's try and verify that. If this was a right triangle, we would have 337, square root of 337 as the hypotenuse. And that would mean that 16 squared plus 19 squared would have to equal 337. Is that indeed true? 16 squared equals 256. 9 squared is equal to 81. And that indeed does sum up to 337. Wow, that's a really nice coincidence. So we know that the height of this tetrahedron now is 16. All right, let's go back to our previous slide. We know that that base triangle, BCD, has an area of 108. So now we just need to multiply this by 16. And then the formula for the area of a tetrahedron now, we just have to divide this by 3. So when we divide by 3, we get 108 divided by 3 is going to be 36, I believe. 36 times 16 is equal to, I'm just going to do some quick mental math here. This is going to be equal to 576, I believe. All right, so 576 hopefully is our answer. I do see a lot of people saying that in the chat. And we check our answer, and indeed we have 576. So great job, everyone in the chat, and I'll pass on the next question to Eric.
All right, yeah, that was really nice how everything worked out. Okay, so now sprint round number 23 is going to be a long one. So to read this question, let n be a positive integer, and the integers from 1 to 2n inclusive are going to be placed in a grid of unit squares with 2 rows and n columns, such that each unit square contains exactly one number. And then we're going to let an be the number of ways to place these numbers into the grid, so that the number in each unit square is greater than the numbers in all of the unit squares to the right of that number in the same row. And we're also going to let bn be the number of ways to place the numbers into the grid, so that in each column, the bottom square contains a greater number than the top square. Alright, so, and finally we're going to have what is the smallest possible value of bn divided by an, expressed answer as common fraction. Okay, so let's see, to think about this problem, let's consider what happens. I think it's nice to do an example real quick. So let's let n equal to 3. So n equal to 3. And let's see what happens when we try placing the numbers 1 through 6 into this 2 by 3. Alright, so we have the numbers 1, 2, 3, 4, 5, 6. Okay, so really we could go like, we just want to choose 3 numbers for the top. Oh yeah, okay, so sorry. Let's first look at an. So looking at the case where any unit square has to be greater than all the unit squares to the right of it in that row. Let's start with, for example, like 2, 5, 6 in the top row. And we notice that once we choose 2, 5, 6 in the top row, the bottom row is immediately set to be 1, 3, and 4. Alright, so if we want to put 2, 5, 6 in the top row, what we notice is that there is actually only one way we could put that in the top row, right? Because we have to have each number be greater than the numbers to the right of it. So in other words, that means the numbers are ordered biggest to smallest. And if you're familiar with ordering numbers from biggest to smallest, there's only one way to do that, right? So immediately once we choose 2, 5, and 6, we have to put 6, 5, and 2 in that order, and then we have to put 4, 3, and 1 below it. So it doesn't actually matter. That we're like choosing these numbers and we can put them in like any way we want into this box, because there actually isn't that many possible ways. There's only one. And so what that means is that an is just going to be equal to the number of ways we could choose the 3 numbers for the top row, because after we choose the 3 numbers for the top row, the bottom row is immediately set, and our ordering is immediately set as well. So that's going to be equal to 6 choose 3 ways. Alright, okay, and now we can probably generalize this a bit, because if we had the numbers 1, 2, 3, ... 2n, and we had a grid that was 2n long, just n long, then we could do the exact same thing, right? Because once we choose n numbers for the top row, the bottom row is set, and the order is also set. So that finishes up an for us. An is always going to be equal to 2n choose 2n choose n. Alright, okay, so now I get the feeling that Bn is going to be simpler because we're only dealing with comparing 2 numbers in each column. So let me go to a new page for that. Alright, okay, so this time Bn is going to be where each unit square in the top row has to be greater than the unit square below it. And when we I'll just go straight to the general case here. Let's see, and let's say that this is n long. Alright, and so we could really do the same thing, right? Because once we choose the number in the top, once we choose the 2 numbers in each column, there's only one way we could put them, right? Whichever one's greater we put on top, and whichever one's smaller we put on the bottom. So that's just going to be 2n choose 2 times 2n minus 2 choose 2 times 2n minus 4 choose 2 ... Right, because so in this case I'm just choosing 2 numbers for each column. Alright, okay, I see this might be a little bit tough in the chat, so I'll try my best to explain this one more time. So we have the maybe it's best to do example. Alright, so we could do the 1 through 6 example again. 1, 2, 3, 4, 5, 6. Alright. Oop. That might have got a little bit cut off there. 3, 4, 5, 6. Okay, so the reason we want to group these into pairs is because once we do group them into pairs, they can only go into the columns in one way. So what I mean is, let's say we choose 1 and 3 to go in our first column, then let's do, I'll change colors. Then I'll go 5 and 6 for our next one, and I'll go 2 and 4 for our last column. So in this case it goes green, white, blue. And when we do that, once we have 1 and 3 together, once we know that 1 and 3 is going to get fed into this first column, there's only one way we could put it. We have to put it as 3, 1, because we have to have the top row greater than the bottom row. And so it's going to have to go in as 3, 1, and then the next one, which is 5, 6. So once we feed 5 and 6 into it, we're going to have to put 6 on top. So it has to go as 6, 5, because the top one has to be greater than the bottom one. And it's the same thing for 4, 2. Putting 4, 2 in it, we have to have 4 on top and 2 on the bottom. Alright, and to generalize what we just did, once we go to the possibility where we have 1, 2, 3, ... 2n numbers to go into our grid, all we need to do is split them into pairs, like put 2 numbers in the first column, 2 numbers in our second column, 2 numbers in the third column, dot, 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 and that's going to immediately determine our grid. So that's just going to be equal to this 2n choose 2 times 2n minus 2 choose 2 times 2n minus 4 choose 2, etc., etc. Okay, so that's going to be equal to bn. Alright, okay, and now we're not even done yet, because the problem is going to ask for what's the smallest possible value of bn divided by an. So we're going to have to do some inequality stuff. And so to go on the new slide, to real quick summarize what we have so far, an is equal to 2n choose n, and bn is equal to 2n choose 2 times 2n minus 2 choose 2, dot, dot, dot. And now these binomial coefficients are going to be kind of clunky to work with. So what I want to do is I want to turn it into an actual fraction that we could work with. So 2n choose 2 is equal to 2n factorial divided by n factorial times n factorial. And then this thing is going to be 2n times 2n minus 1 divided by 2 times 2n minus 2 times 2n minus 3 divided by 2, and it just keeps on going, right? And what we notice is that it's going to be 2n times 2n minus 1 times 2n minus 2 times 2n minus 3, dot, 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 dot. That's going to be 2n minus 2 factorial as well. And on the bottom, we're going to have n2, so that's going to be 2 to the n. Okay, wow, this is getting pretty complicated. So to finally compute our fraction, an over bn is going to be equal to, sorry, I realized I did make a mistake over here. Bn is actually going to be equal to 2n factorial divided by 2 to the n. And then so dividing an, which is 2n factorial divided by n factorial squared, we're going to divide that by 2n factorial divided by 2 to the n. It's going to be equal to, the fraction is going to be equal to 2 to the n divided by n factorial squared. And all I did there was cancel out the 2n factorial. Alright, okay, since we want to minimize, wait, that was the problem, right? Yeah, okay, so since we want to minimize that expression, oh, I did make a mistake. We're actually trying to minimize bn over an. So bn over an is equal to n factorial squared divided by 2 to the n. And since we're trying to minimize this expression, what we want to consider is when n factorial squared is like significantly smaller than 2 to the n. Or we want to make it as small as possible compared to 2 to the n. So like way less than 2 to the n. And we know that n factorial squared is going to be strictly increasing, so I think for this we could probably just start plugging in variables, plugging in possibilities for n. When n is equal to 1, we're going to have the fraction be equal to 1 over 2, 1 over 2. Then when we plug in 2 factorial is 2, squared is 4, divided by 4. Wow, okay. So, and then plugging in 3, that's going to be 6 squared 36 divided by 8. So that's going to be 9 over 2. And it seems it's like it's going to just get increasing from there, get bigger from there, right? Because we know n factorial is going to get bigger at a faster rate than 2 to the n. Okay, so that was a really long question. Hopefully the answer is then 1/2. Alright, and we could check our answer on that. Yep, okay, so the answer is indeed 1/2. Sorry that took a really long time. I'll pass it back to Luke now.
Yeah, really good job, Eric, on that marathon of a problem. But you did indeed get the right answer, which is really cool. All right, so now on to the next problem, which I do not think is going to be that much easier, unfortunately. What is the sum of all integers x with the property that the value of x times x plus 1 times x plus 2 times x plus 3 plus 1 is the perfect fourth power of an integer not necessarily distinct from x? All right, so I'm just going to outlay a general overline of what I'm going to be doing in this problem to solve it. So we see that this this expression is going to have an x to the fourth in it, right? That's the first thing I noticed. So I think we can kind of do casework here. We can say, what happens if this perfect fourth power is x? Then what happens if this perfect fourth power is x plus 1? Then what happens if this perfect fourth power is x plus 2? And then keep on going from here. And we can just solve the problem this way. We can also go negative, so we could do what happens if this perfect fourth power is x minus 1 relative to this, and then we solve it to figure out exactly what x is going to be. Yeah, and then we can sum up all of those x's, and that will give us our answer. So this is kind of what I'm going for. All right, the first thing I'm going to do is x because that makes the most sense. But before that, I'm gonna expand this entire expression over here. So when we do that, I'll just sort of do it a little quick here. X plus 1 times x plus 2 is equal to x squared plus 3x plus 2. And x times x plus 3 is equal to x squared plus 3x. Now when we multiply these together, we get x to the fourth plus 6x cubed plus, hopefully I'm not going to make any mistakes here, that would be bad, plus 11x squared. And finally at the end we have 6x. I really hope that is correct. I think it is. And then finally at the end we have another 1 added on to the end. So this is our expression. I'm going to start a new slide because everything is going to become very crowded very quickly. So our expression is equal to x to the fourth plus 6x cubed plus 11x squared plus 6x plus 1. And then the first case we have is when this is equal to x to the fourth. So when this is equal to x to the fourth, then we have 6x cubed plus 11x plus 6x plus 1 equals 0. And we want integer solutions to this. So maybe there are no integer solutions, but I think we can hopefully find one. So there's this really cool thing called the rational root theorem. And I don't know if any of you guys know it, but the rational root theorem says that if any of the roots to this equation are rational, and rational means real and just not unreal. Yeah, the real. All right, so if any of these roots are real, then they're always going to be some form of this number at the end divided by this number over here. And that sounds very vague, but what it really means is that it could be 1, it could be -1, it could be 1 over 2. And the reason I'm getting 1 over 2 here is because this 6 over here has a power of 2 in it. So it could also be 1 over 3, or -1 over 2, or -1 over 3, or 1 over 6, or -1 over 6. If this is still a little confusing to you guys, you can always just look up the rational root theorem online, and that will have good explanations for you guys, because I think it's something that you guys should know in general. All right, so keeping that in mind, the only integers that could possibly satisfy this equation for x are -1 and 1, because this value over here is 1. So plugging in 1, obviously going to be something that's positive and not equal to 0. So -1, however, is going to give us an integer. I mean, -1 is going to satisfy this equation. And the reason why that is -6 plus, sorry, oh, I forgot to add the squared here. -6 plus 11 minus 6 plus 1, and this is indeed equal to 0. So one of our answers is going to be -1, and that is when x to the fourth is equal to that entire expression. You can verify for that for yourself. I'm not going to. All right, our next case is when x to the fourth is equal to, sorry, not x to the fourth, x to the fourth plus that entire expression. X to the fourth plus 6x cubed plus 11x squared plus 6x plus 1 is equal to x plus 1 cubed, x plus 1 to the fourth, sorry, or I'm just going to simplify that, x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. And when we simplify all of that down, we're going to get 2x squared, 2x cubed, sorry, 2x cubed plus 5x squared plus 2x is equal to 0. So obviously x equals 0 satisfies this expression. So when x is equal to 0, then we get, sorry, let's just factor x out of this first. Then we get 2x squared plus 5x plus 2. And we can factor this remaining expression, and that would give us x times 2x plus 1, I believe. Yeah, 1. And multiply that by x plus 2. And when you multiply that out, I think you get the correct thing. So this leaves our answer for this part to be equal to x equals negative 2. And the other one is going to be fractional. It's going to be negative 1/2, and we only want integers, which is why the rational root theorem is so powerful for this. So now we're going to get negative 2 this time. All right, now we have a couple more cases to try here. All right, one more case, and then we'll go on to the negative exponents. So x to the 4th plus 6x. No, that wasn't the thing, was it? It was the thing. 6x cubed plus 11x squared plus 6x plus 1 equal to x plus 2 squared. And when we do x plus 2 squared, what we get is x to the 4th plus plus 8x cubed plus, it's a little bit difficult, 24x squared, I believe, plus 32x here, and then plus 8 at the end. No, 16, sorry, 16 at the end. Yeah, 16 at the end. All right. Plus 16 at the end. And now what we get is we're going to get, if we move all this to the right-hand side, then what we get is 2x cubed plus 13x squared plus 26x plus 15 is equal to 0. Now we can use the rational root theorem again to say that the only possibilities for this are going to be negative 1, negative 3, negative 5, or negative 15. All of the positives won't work because it will just remain positive. So let's just try negative 1 first. Negative 1 is going to give, obviously, it actually doesn't matter because we already have negative 1 as one of our answers. So let's try negative 3, actually. Negative 3 is going to give us negative 27 times 2 plus 13 times 9 minus 26 times 3 plus 15. And if we multiply all of this out, this is a little bit difficult, but we can change this to be equal to 13 times 3 because 26 equals 13 times 2. And then add 15 to that. And that's going to be 39 plus 15, which is equal to 54. So indeed, negative 3 is also going to be an answer of ours. So going back up, we do indeed have negative 3 as an answer as well. And this seems very tedious, though. It seems as if there could be a little bit of a shortcut here. Why is it that we have to multiply all of these things out in order to get, it seems like we wouldn't actually have to multiply out the x plus 3 and then solve this really difficult equation. Oh, sorry, I'm on the wrong page. That one's not that difficult. This one's really difficult. Multiplying x plus 4 out, x plus 2 squared out is very complicated, and then solving this is also really difficult. So that's not something I want to do. So I kind of want to take a shortcut and see, is there anything that could be a little bit easier for us to do? And maybe there is. Something I noticed when I was looking back at this problem is that these 4 numbers are consecutive numbers. And when we were looking at these, we said they can go anywhere they want. They can be positive, negative, it doesn't matter. So it doesn't really make sense that we would solve all of these because sometimes some of these are a little bit of duplicates. For example, when we take x plus 1, x plus 2, x plus 3, x plus 4, if we make sure that these are equal to these, that's not necessarily going to give us our answer. We have to kind of use this fact that these are consecutive numbers to help us solve this problem. And the reason why this is going to help us is because, for example, let x equals negative x, for example. So then we have negative x times negative x plus 1 times negative x plus 2 times negative x plus 3 plus 1. And what happens is that we're just multiplying 4 consecutive numbers, and it doesn't matter what the order is. But when we take all of these over here, all of these x plus 1, x plus 2, and try and test these cases for this problem, it doesn't really matter where we are as long as we have covered more than half of these numbers and we have gone to the halfway point, because we can make these numbers negative. And when we make all of these numbers negative, in fact, these numbers are the ones that are big and these ones are the numbers that are small. So we're going to have covered all of the cases that we need to cover if we have just gone through x, x plus 1, and x plus 2, which we have just done. So going through all of those cases, the three numbers that we got were -1, -2, and -3. So summing all of those together, we get -6. And hopefully, I believe that is going to be the answer. And I'll check my work here. And the answer is indeed -6. So I believe we got the correct answer, and I'll pass it on to Eric for the next problem.
All right. Actually, though, I think we might be at the end of our session because unfortunately it is 8 o'clock. But that was a crazy problem, Luke. That was a lot of polynomials, so nice job on that. This day has been full of these really long problems. But yeah, that was a pretty awesome live solve if you would ask me.
Yeah, that was a lot of fun. Thank you guys for all tuning in. It was such a pleasure doing math with you guys. So hope that you guys maybe enroll in a course or watch another live solve. But if not, see everyone next time. And thank you guys so much for watching.
Yep. See you, everyone. Thank you.